So the next order n squared algorithm that we're going to look at is called insertion sort. This is also an order n squared or a theta n squared algorithm. Again, I repeat, when we talk about big O here, we're essentially looking at the tightest upper bound. And what does sorting by insertion mean? Let me take an example again. And insertion sort is very similar to what you would do, somebody, when you play cards and somebody deals out the cards to you. How do you organize the cards on your hand? When you pick one card at a time, you essentially perform what's called insertion sort. And let's see how we do this. Let's say these are the elements. Again, we assume that the array starts from A of 1 to, in this particular case, A of 8, 1 to n. And let's say we have the same numbers, 8, 14, 41, 3, and 39. The first step, what we do is we find the location of the first step, find the location of the most minimum element in the array. In this example, it is located as location 7. And then what we do is we exchange it with the first element. Swap it with the first element. So what do we do here? 3 will go here. We'll have 35, 18, 8, 14, 41, 20, and 39. So now let us look at this array. Now what happens is this process of putting the minimum at the beginning divides the array into two parts. One which is sorted and the other which is unsorted. Then what do we do? So one pass through the array, we found the most minimum element and then exchange the most minimum element with the whatever was the first element in the array. And this divides the array into two parts, one consisting of sorted portion and the other consisting of the unsorted portion of the array, as we just now saw. Okay. Now what we do is through next, now we insert this element 35 into its position in the sorted portion of the array. Interestingly, we find that it is in order. So because I can just, there is, since 35, since this is a sorted portion and 35 is larger than 3, it is in the correct position with respect to 3, and we augment the sorted portion of the array. Next we have 18, 8, 14, 41, 20, and 39. So now this is the new length of the sorted portion of the array. This is sorted. Now we find out where to insert 18. Okay, and so what do we find? We essentially, 18 has to come between 3 and 35. So we push 18 here and put 35 here. 8, 14, 41, 20, and 39. So this is the new sorted portion of the array. Now let's see how to insert 8 into the sorted portion of the array. Notice that what happened now, it has to come between 3 and 18. So we move the elements 18 and 35, and you put 8 over here, 3, 41, 20, and 39. So now you have 4 elements corresponding to the sorted portion of the array. Now for the next element, what do we do now? Again, push it here. So you have 3, 8, 14, 18, 35, the new sorted portion of the array, and so on. Okay, so if you look at the algorithm, what are we doing? We have the array divided into 2 parts, the sorted and the unsorted portion. Then what do? We take an element from the unsorted portion and insert it in its appropriate place in the array. Okay, so let us see how this algorithm looks like. So we have, again, let me call it a procedure module because we're doing it in place. There's nothing that the function is returning. Let me call this insertion sort. And let's say I have an integer array and the length of the array. And let's say I have variables int I, increasing index of elements ordered at each stage. Let's see what this means as we keep on, when you have look at the sorted portion. Okay, every time we are increasing it by 1. So you need a pointer for that. This is decreasing index to search for the position where an element is to be. When you're augmenting the sorted portion by one element, where should that element be inserted? And J keeps track of that. Int P, original location of the minimum element. Most minimum element. We'll see why we are doing this, okay? It's just like a sentinel. And index is the current element from the unsorted portion that must be inserted in the sorted portion. Okay, let me just, they're all comments, okay? Just to tell you what kind of variables we have in using in this. Okay. So now, what is the objective? Sorts an array in non-decreasing order. We don't say increasing order, but we say non-decreasing order again. Why? Because they can be repeated elements. We assert, assuming that array starts with 1, n greater than 0, and I equal to 1. Why? Because the sorted portion of the array is starting with 1. Okay. Can assert this. That means what? This is the sorted portion of the array. We assign first, assign the value of a of I. P is assigned the value of 1. And for I going from 2 to n, do if a of I less than first, then P is assigned the value of I, and first is assigned the value of a of I. End of. So this is the usual, finding the minimum element. Then we place a of P, a of I, and a of I is assigned the value of first. Sorry, a of 1. A of A is assigned the value of a of 1, and a of 1 is assigned the value of first. So this gives us the first sorted portion of the array. Now we'll write loop invariant a little later. For I going from 3 to n, do. So this is why that sentinel, so a of 1 is like a sentinel, okay? We'll see why this is important. So whenever you're coding, this is something that you will always see. You do some kind of a pre-processing to ensure that some checks need not be met. What we can do is X is assigned the value of A of I, so third element is taken into account because we know that 1 and 2 are already belong to the sorted portion of the array. That is, we can say that the loop invariant is going to be something like this. 1 less than or equal to I less than or equal to n, and A of 1 dot dot I is sorted. Okay, you can easily claim this. 1 and 2 are elements which are sorted. Now what I can do is, while I've got to do something else. I do a j is assigned the value of I. While x less than a of j minus 1, do a of j is assigned the value of a of j minus 1. So this is what we did here, to remember it. Notice that I need to insert 14 here. So I move 35 and I move 18. Then this space gets emptied and I push 14 over there. Okay, that's what we're doing. Finally, then we set a of j is assigned the value of x. So what can we have here? And y. So now what can we see here? One, sorry, there's something that's missing here. Sorry, j is 1. Let me erase this. One statement is missing. A of j is assigned the value of j. I forgot to decrement the variable j here. And y. And what can we assert now? 1 less than or equal to j, and we can also assert that x is less than or equal to j plus 1 dot 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 I. Okay, because we're taking the ith element and inserting it into its position over here. Once this is done, we assign a of j to x, and then we close the for block, end for. Okay, and once this is done, we can claim that 1 dot dot n is sorted in non sorry, in non decreasing order. Okay, and end module. Okay, so this is what the insertion sort algorithm is all about. The for block and the while block actually finds out the location in the sorted portion where a new element from the unsorted portion has to be inserted. Then we just move all those elements up, okay, till the position of the new element x is found, and then you place it in its appropriate position. Okay. Let's do an analysis of insertion sort. Where is the comparison done? Comparisons is defined by x less than a of g minus. And the other expensive computation is the number of times array elements need to be moved. Need to be moved. Okay. And the for loop is executed once for every I. That means n minus 2 times. Okay. What is the smallest number of comparisons that are there? Let's look at the best and the worst case. Best case, for example, we do n minus 2 comparisons, and computing first, we perform n minus 1 comparisons. Okay, that means what? The total is n minus 2 plus n minus 1, which is equal to 2n minus 3. Okay. Worst case, let us look at it. I minus 1 comparisons for each I. Okay. And this will turn out to be, so you get something like, and of course you have the n minus 1 for computing the first. So this will turn out to be n plus 1 into n minus 2 over 2 plus n minus 1. How does this come from? For 3, you can have 2 comparisons. For 4, when I equal to 4, you have 3 comparisons, etc. N, you have n minus 1 comparisons. This is where this analysis comes from. And in the worst case, we get n squared plus n minus 2n minus 2 plus 2n minus 2 by 2. This becomes n squared, this goes, n squared plus n minus 4 by 2 comparisons. So you could have also solved this by using the sum rule and the product rule, but I just wanted to give you a detailed analysis. Therefore, in the worst case, this is a theta n squared algorithm. Okay? Insertion sort is also. But insertion sort is nevertheless preferred over the bubble sort, because in exchange, for example, when I say T is assigned the value of A is assigned the value of B is assigned the value of T, this are all memory access based operations, which are considered to be very expensive. So this comes to a conclusion on the type of order n squared algorithms that we have. We'll also do quick sort, which is the worst case our order n squared, but that depends on the permutation of the data, taking a particular permutation which is most improbable. And there's another variety of large number of varieties of sorting algorithms are there. There's something called shaker sort, where there's a variant of bubble sort, and this one has what you do is you bubble from left to right, and also next bubble from right to left. Then there's something called shell sort, and takes an array, makes multiple chains like this, and it will, for example, if I'll make 4 chains initially, I'll do insertion sort on each of the 4 chains, and then this will be the one pass. And next pass, it will form a chain with like every alternate element, and then will be 2 chains now. See, and finally we put them all in place with, and everywhere what you're doing is each pass, or for each chain you're using insertion sort to put the elements together. So these are all many variants of sorting algorithms that we have. They're all simply varieties of the order n squared algorithms. Small differences, and best way to find out which is the best algorithm is on some random data. What I would advise you to do is take large number of, randomly generate a whole lot of data, fill an array, run the sorting algorithm a number of times, count the number of exchanges that are there, average it over many such batches to get actually the actual running time of the algorithm for different types of sorting algorithms. Okay, so this completes the order n squared algorithms that we talked about. Let's stop here, and